Okay, let's just jump right into this. Welcome to our latest explainer. So, if you've ever opened up a classic introductory electrical engineering textbook, stared at a page completely covered in dense formulas, and literally felt your heart rate spike, yeah, you are absolutely not alone. Honestly, it can feel like you're standing in front of this giant, impossible maze with zero map to guide you. But right now, we're going to take a collective deep breath, we're going to step back. Together, we're going to peacefully unpack the fundamental concepts of circuit regulation and efficiency. We'll use the actual source material to guide us, and we'll turn those super intimidating pages into clear, bite-sized steps.
I actually want to kick things off today by throwing a gentle but honestly fascinating question your way. Why exactly does pushing a system for maximum power always cost us half of our efficiency? As we dive into the textbooks, you'll see this built-in natural paradox in physics. It turns out, giving 100% effort doesn't actually guarantee a 100% efficient result. No way. It's this beautifully balanced law of nature that kind of surprisingly mirrors our exact lives as students just trying to get everything done.
But hey, before we even look at a single textbook diagram, let's look at the human side of things. These are a real student's actual handwritten notes on the fundamental properties of charge, current, and electrical potential. I really love starting here because it just builds so much empathy, right? Behind every single intimidating printed formula in those giant heavy books, there are literally just people. Just human beings sitting at a desk with a pen trying their best to understand the basic natural flow of the universe. The source material is really just a record of that exact human curiosity. So let's look at how those handwritten notes define our two absolute most foundational concepts. And we're going to keep things wonderfully simple here. Voltage, or electrical potential, is really just the amount of work required to move a charge from point A to point B. Think of it as the push, or the effort. Current, on the flip side, is defined as the rate of flow of that electric charge. So if voltage is the push, well, current is just how fast the things getting pushed are actually moving. Separating these two ideas calmly like this just instantly strips away the confusion. You've got the push, and you've got the flow. That's the whole shebang. Now, when we bring those two simple ideas together, the student's notes define electrical power. We see the super famous equation, right? P equals V times I. Power equals voltage multiplied by current. Now, I know sometimes equations look like these scary hurdles, but just read the plain English written right below it, the rate at which work is done. That is literally all power is. It's just a way of measuring how much active work a system is doing. You just take the push, the voltage, and multiply it by the flow, the current. Simple as that. Section 1, regulating the flow, finding the right balance in the circuit. Let's get into it. Okay, so now that we've got a handle on the raw basics of push, flow, and work, we gotta ask, how do engineers actually tame this energy? Because we don't just want raw, wild power, we want useful, directed power. And that brings us to regulation. A massive tool for this is voltage division, and it happens in 3 super intuitive steps. First, you connect resistors in series, which just means putting them one after the other in a single path. Second, the total voltage, the total push of the entire circuit, is shared among those resistors. And third, the voltage drops proportionally across them. It's honestly just a natural way of sharing a really heavy workload. It's like if you and 2 friends are carrying a giant couch, the total weight naturally divides among the 3 of you based on how much of the actual load you're physically holding up. To really ground that concept, here's a visual diagram pulled straight from the textbook. It's showing a basic voltage divider circuit. You can see the main source voltage over there on the left, right? And it's pushing through 2 resistors, R1 and R2, lined up right in a row. Now, the textbook shows us that the dense equation above it is actually just a formalized way of calculating that exact naturally shared workload we were just talking about. We can precisely dial down a voltage to whatever smaller size we need, literally just by picking the right size resistors to share the burden. So here's the crucial takeaway. While voltage divides up in a series circuit, current division does pretty much the exact same job for parallel circuits. The textbook pages here show how the flow splits up when it has multiple different paths it can take. But instead of dropping proportionally, the flow splits inversely based on resistance. It's actually a lot like a huge crowd leaving a concert stadium through several different exit doors. The crowd smoothly, naturally divides, right? Way more people are going to take the widest, most open doors, the path of least resistance, and way fewer people are going to squeeze through the narrow, restricted doors. It's just this perfectly elegant, natural regulation of flow.
All right, moving on to section 2, the efficiency paradox, pushing for maximum power transfer.
Now, this brings us to what I think is the absolute most fascinating and honestly the most relieving concept in the whole textbook. It's where the math of electrical circuits teaches us this incredibly profound lesson about the nature of output. Looking directly at the math from the source text, engineers often need to squeeze the absolute maximum power out of a source and deliver it to a load, like a giant speaker or a radio antenna. To pull that off, they match the resistance of the source perfectly to the resistance of the load. But, okay, look really closely at the bottom line of that calculation. The symbol for efficiency, eta, equals PL over PS, which resolves to exactly 1/2, 50%. The math literally proves that to get the absolute maximum power out of a source, your efficiency drops to exactly 50%. Half of the energy is completely lost as heat inside the system itself. Mind-blowing, right?
And this slide just brilliantly illustrates that harsh reality. On one side, you've got maximum power output. On the other, a strict 50% efficiency limit. This striking visual contrast really hammers home the point that achieving maximum output means you are fundamentally losing half of your efficiency. It is a stark, absolute reminder from the physical world that maximum effort is just not always optimal. To push the hardest you possibly can, you literally have to sacrifice half of your energy just to sustain that push.
Let's look at another page from the source text to see how real-world engineers actually handle this. The text talks about impedance matching. It explicitly states that this technique is used in electronic circuits where output power is the absolute chief concern, quote, though the power transfer efficiency is reduced to 50%. It's just an accepted reality. Engineers knowingly accept this massive 50% loss as the absolute cost of doing business when brief, intense bursts of maximum output are the only goal.
But what if you actually want a system to last a really long time? Look at this direct quote from that exact same page. Efficiency is of paramount importance in power circuits which operate far from the condition of impedance matching. See, when engineers are designing those massive power circuits, like the ones that literally run our cities and keep the lights on, they care about longevity. They absolutely prioritize efficiency. So what do? They intentionally operate them far, far away from that maximum edge. They regulate the flow so that it's sustainable, not just so it spits out the highest possible immediate output.
So let's bring this whole engineering principle right back to your daily reality as a student. Call it a law of balance. We literally just saw the math. If a physical, real-world electronic circuit loses half of its efficiency and generates massive amounts of wasted, useless heat when it's pushed to its absolute maximum limit, well, it's pretty much a law of physics that you probably will too. Pushing yourself for absolute maximum output all the time inevitably leads to wasted energy and total burnout.
Which leaves us with this final peaceful thought to kind of reflect on as we wrap up this explainer. Are you optimizing your study habits for maximum immediate output, like cramming all night long and burning half your energy as pure stress? Or are you actually optimizing for long-term efficiency? Just remember those city power circuits that run the world. They intentionally operate way off the maximum edge, just so they can run smoothly and efficiently forever. You really don't always have to operate at maximum capacity. Honestly, sometimes finding the right resistance, regulating your flow, and just pacing yourself is the smartest, most mathematically sound way to succeed. Thank you so much for joining me today. Take care of your circuits out there, and I'll catch you next time.